He worked on the theoretical foundation for virtual element methods. So recently, Shuhao got his faculty position at Washington University in St. Louis, and he's working on some models in the machine learning. So today, Shuhao is going to give us a talk entitled Galerkin Transformers. So please join me in welcoming Shuhao.
I would like to thank the host for giving me this chance to present some of my recent research. Actually, I started this research as like a side fun project. It's because I'm mainly a finite element guy, and this is actually my first project on machine learning, like a research. So, and this is how this research got started. So basically, last October or November. So Long, who was my postdoc mentor, Long sent me an article in Chinese. So it's this one. It's this article in Chinese. And Long asked me, okay, so Shuhao, can you read these Caltech group's paper and the report in the group meeting? So I said, okay, sure, why not? So I went, so I read their paper, and I re-implemented their code. I was totally blown away. I thought it was a simple idea. I'm just curious, like, why people haven't realized it earlier. So the idea is pretty simple. Basically, it's like a simple regressor in the frequency domain. So so I stole this image from their paper, and what happens here is they have some input function. They do this Fourier transform, and they have all these bandwidth, like representation in waves. And this one is a learnable weight. As we can see, this learnable weight cuts off certain frequency they don't need. And after that, the inverse Fourier transform will combine with this. This one is like a ResNet, this skip connection structure. And after they add together, this is a nonlinearity. So it's pretty much like a ResNet, but the convolution happens in frequency domain. Okay, so, and it's pretty simple. Okay, and this is a question right now. Many people are interested in. So the operator learning related to partial differential equation. So we have mainly two problems. The first problem is related to the parametric PDE. Okay, so first one is we have a parameter, and what we're gonna do is we wanna learn a map that maps this coefficient directly to the solution U. Okay, the other one is if we have the solution and we have certain measurement noises, and we want to get back to A. So this is our first problem. The second problem is if we have a stiff system. Okay, stiff means the error will be propagated through an explicit integrating scheme. So we either use super small time step, or we use a much more expensive implicit scheme. Okay, so for example, so right now, this one, we want to learn an operator starting from initial condition or any like intermediate step, and to a much later time. So so I would like to emphasize this T1 is much bigger than our normal step size. Okay, so for example, bounded by the CFL condition for the explicit scheme. Okay, there are many advantages, like I said here. So there is no retraining. So once we learn the operator, and if the data satisfy certain caveats, like the same distributed and same distribution for the initial condition or the input, then we don't have to retrain. And even for some downstream tasks, like for single PDE, we only need to fine tune the model just like the BERT. Okay, And here is the example I took from the Caltech group's data set. So it's a Darcy flow. So the left here is the coefficient. As we can see, the coefficient exhibits certain random interface. So later we will just, give the mathematical formula of this coefficient of why it exhibits these, island-like structure. So we only have two value of this coefficient. So 12 and 3. But they have this sharp interface and it's random. Okay. And this one is the solution. So what we want to do, or what they had done, is they use this as input and this as output. So last October, I was pretty blown away by this because I'm not a machine learning guy. I'm just a finite element guy. This is out of my, so I don't know how to express like how shocked I was back then after I implemented. And moreover, so what they can, so they call this they call this a zero shot super resolution. So it's a fancy name. Just we can use training data with lower resolution, and we do evaluation on a much higher resolution. So they call it zero shot super resolution. I mean, so but there's a caveat. Okay, so because our output is smooth, our interpolation will preserve this approximation capacity, but it's pretty fancy. Okay, so however, but even though I've never worked in machine learning, but I coded a lot. Okay, I code many this transformer model back then. I mentor like student to participate Kaggle competition, and I realized, hey, this so I recode, I re-implemented the pipeline, and so it's pretty. So at its essence, the pipeline the same as a sequence to sequence model in like a machine translation. Okay, so basically we have a sequence, okay, right here, and we want to give another sequence. So by the way, this F is, like we said here, it's a matrix, and our output is another matrix, and this N is called the sequence length, or if we can think in 2D, it's like more like for example, nx times ny. So and this D is called the latent dimensions in the neural machine translation community, or sometimes they just use this D model to represent this number. So this is normally fixed. For example, in classical transformers, this is 512. And so then, hey, I realized this operator learning is pretty similar to, I mean, when being discretized at a discrete grid, it's pretty much similar to the language models, because language models aims, so especially here. So language models, for example, it can be trained, especially, for example, BERT can be trained on, for example, a sentence with, let's say, 20 words, but the downstream task can be for sentences with like 100 words. So it's pretty nice. Once I realized this, hey, let's do some literature review, see what people are doing with this operator learning thing. It turns out, so this dates back. This is a long list. So here, this is a non-exhaustive list. So if your work is not listed here, so sorry for that. And you can send me an email. I can add another slides to include your work. And so there are lots of work already, using this CNN, deep convolutional neural network. But if we have coded convolutional neural network, it has a huge problem. That is, its input is like fixed. So what I mean is, for example, for ResNet 34 pre-trained on ImageNet, the resolution is 224 square, and similar for efficient net, So for example, efficient net, let's say B3, I don't know. But they have this fixed resolution. For example, I forgot, I think B4 or B3. B3 is a 300 square. And if we get bigger, the resolution can be bigger, but it has to be fixed. So otherwise, if it's not, so once we do this interpolation or sampling, the performance will degrade. Okay. So there are two groups of people aiming to train, this fancy black box model, to remedy this drawback of CNN. So our model shouldn't be at a fixed resolution. The first, so I list is there's a Caltech group. So they claim that in their last year's paper, Fourier neural operator, they achieved this state-of-art performance. And the other is here, right here in our audience, and it's a DeepNet. And basically what happens is I read the paper, even though I don't understand it fully, is to leverage the universal approximation theorem so that we can approximate like a subset of subspace by this the combination of different bases, and we want to learn these bases. And so also I would like to mention that actually the benchmark problem are studied by like many other groups. So this data-driven approach, but not the non-black box model. Okay, so for example, model reduction for the parametric PDEs or some Bayesian approach, so that we can do some trial and error, and let's find the best basis after many iterations, trial and error. Okay. However, so there is something, like I said earlier, there is something that in the sequence to sequence community, so the biggest thing is transformer. Okay. So this paper is Attention is All You Need in 2017 EuroIPS. So here it doesn't show. So in the 2017 EuroIPS, and this is attention is all our need. Okay, so all we need, and it has a fancy title, and it has lots of citations. I think this slides I prepared back in August. So I think this number at least is 28,000 already. So that's just my estimate based on a month extrapolation of citations. So it's pretty crazy. So this is a huge in natural language processing community. It's so right now in NLP, transformer is the only model. So everyone is using transformer. No one uses RNN anymore. So except for like testing or purposes, comparison purposes. So let me just spend a few minutes briefly, introduce what is transformer. And this I copied from Attention is All You Need paper. And so I watched this guy's lecture and video. So Lucas Kaiser, and he was pretty excited about this transformer. So what Google wants to do is they don't want to use CNN anymore. They only want to use transformer. As we can see, all the DeepMind's research right now is about transformer AlphaFold or whatever, the like a DNA sequencing thing, and they were pretty excited. And next slides are so I try to convey the message from Lucas Kaiser and to our audience that why they are excited. So traditional neural network, if we have so here we have a CNN. So CNN is like a sparse connected, so it's like a sparse version of this densely connected network. And then we have this sequential model, which is RNN. And for language model, RNN was the old state of the art. Okay. However, it has one huge drawback. So Google has lots of hardware, for example, TPU. And Lucas Kaiser said, actually, I should change this to TPU. So Lucas Kaiser said, this RNN model is kind of, not so big. So they want bigger models that can fully saturate the TPU. But then they found, no matter how we increase the size of the RNN, it cannot saturate the TPU. Why? It's because this operation is sequential. In order to get the hidden representation in next time step, we need all these, all the input from previous time step, as well as all these hidden states computed by, our cells. For example, this is either GRU or STM cells, and so it's a sequential operation. In order to get this, we have to wait. I'll say we have to wait our GPUs in a cluster to finish all these tasks. It's not ideal. Okay. So then Google invented a model such that it can fully saturate the TPU. So the temporal dimension, this long range time dependencies, does not have to happen in a sequential way. And this is the transformer. So I took this figure from Attention is All You Need. It has many components, and I want to emphasize that up till like maybe say earlier last year. So these components are all deemed indispensable. So no one changed like a single of these components until last year. And everyone is just using it and thought, because like I said earlier, removing a single component will cause the model, degrade like huge in the, for example, in the simple translation task. And so let's consider this part. This is the encoder part. Okay, so we don't need the decoder because the decoder is more like for translation tasks. So we only need the encoder part. Encoder is this essence is a sequence to sequence model, and the key is this multi-head scale dot, attention. So to better serve our community, I reproduce this figure. So this is for single head. So let's consider just a single head. What happens here? First, we have this latent representation. This is a matrix, okay, of n by d. So n is our sequence length, and d is our latent dimension, and our output is of the same size. All right, and then we have all these fancy, blocks doing operations. And I want to mention that the purple one having the biggest number of trainable weights. So this is trainable, but it's the most weights are here. Okay. So once this input goes in, it multiplies with 3 trainable matrices. They call the projection matrices. We get the key query value. Okay. And after that, we do this scale dot product attention. And after this matrix multiplication, the softmax is applied row-wise so that each row sum up to 1, and then multiply with this value so that there's a new value, or say, is a convex combination of the old values. All right. And this adds just a skip connection to, so that we can stack all these layers deeper and deeper. It's like a ResNet. And after that, we have our full attention operator, especially this G is a nonlinearity. And the Google just choose a 2-layer fully connected neural network as a nonlinearity. And this is our attention operator. So if we analyze, or say we benchmark, or say we profile each layers, and what happens in each layer, in each variable. So I profiled it. I found, hey, this softmax is pretty nice. So I think this is mentioned in literature as well, but I couldn't find the exact reference. So the softmax basically tames down. Keep in mind, we have 2 trainable matrices multiplied together. And in traditional neural network, layer-wise, so if we have this, normally we have only 1 trainable weight, the other is the output from previous layer. But right now, this matrix product is very explosive in terms of gradient. So the softmax helps, it achieves much better numerical stability. And that's why they add all these layer normalization to help this numerical, to help the training to get stable. I think this already studied in some concurrent work mentioning that this is indispensable, especially the layer normalizations. Okay. And so even though transformer has much more parameters than RM, but it can fully saturate Google's TPU. So it's a huge bonus to them. And originally I thought multi-head attention is orthogonality, but later on I changed my perspective after I extract the latent representation. I found even though they are independent, but they are not that orthogonal unless we exert certain operation to impose them. So now here's a question. Once we know the transformer is the state of the sequence to sequence problem, and the operator learning problem when discretized is a sequence to sequence problem, can we apply transformer to some simple benchmark problem? So this is a question we would like to ask. So we consider the simple Burgers benchmark from the Caltech group's paper. And I mean, it's not a difficult problem to solve. We have Burgers equation and it's viscous. We have a pretty huge viscosity here in that it will make the initial conditions smoother and smoother. And this is our operator we aim to learn. So this is our initial condition. And this is the solution at time step 1. So it's basically like an integrator. So this is a nice benchmark problem. I mean, I would like to mention that this problem is not difficult. Okay, so the input here is basically.
Sorry. I have a question. Why did you? I mean, you seem like very inquisitive mind. Did you ask a question why they, for this simple problem, instead of 50 points or 100 points at most, why do they need to do 2,048 points and 8,192 points? It's like taking a big tank to kill a bird. Why do they do that?
Yes. That's a good question. So
why didn't you suspect them?
Yeah, that's a good question. I actually, that's a very good question. So it's a low dimension.
We do that in the homework. In the homework.
But the thing is the initial condition. So in the next slides, we'll see that the initial condition still has these these fine structures that only finer grid can resolve.
128 points. I will increase my number to 128 points.
The 128 points can enough capture the final solution at time equals 1. But the initial condition still needs this final, like a finer structure.
Okay, keep going.
Mm-hmm. So this is our initial condition. So it's sampled using Gaussian random field. And this is our final solution at time equals 1. As we can see, the viscosity smooths the solution a lot. So we kind of try to design a simple, like similar to the language model. We have our encoder, we have our decoder, and we have our attention. So basically, we try to apply the natural language model to this simple benchmark problem, see if it works. The answer is it doesn't. So I tried, basically, I called the PyTorch transformer module. So I called it, and as we can see, so this is the Caltech group's original result. This is my re-implementation, and training 100 epochs, and this is a transformer applied directly. And it was bad. So I only took the encoder. The transformer has about 40 million parameters. And I only took the encoder, so half of it, half of the parameters, and it's not very good. So so then it was the end of the story back in the last November. Okay, so I said, I got frustrated. I said, hey, these natural language people, they invented such a huge model, and it's only for natural language. Is it only for natural language? So then this February, so I restart this project, like as a side project. So I started reading all these literatures about transformers and how the people understand it. And I think no one really dissect the transformer, the scale dot product, this attention, component wise. If we dissect it component wise and we ignore the softmax, we can see we can rewrite it. And moreover, we treat these. So this is like a column. Sorry, this is a row wise. Like dot product. So if we rewrite, or say if we reinterpret this as, so with this sum, like a Riemann sum, we reinterpret this as integral. This is pretty much like a learnable integral transform with 3 trainable, what they called, what the natural language processing people called, sorry. So this one as a feature maps. All right. And then I said, hey, because so then I profile the model, the softmax, consume the most memory, consumes the most flop, and consume the most like CUDA time. So I said, why not just to remove it? Because if we have this learnable, this is like a learnable Fourier transform, why not we just use Fourier neural operators architecture? Because Fourier neural operator doesn't have softmax, and Fourier neural operators spectral convolution, they have this matrix and this matrix like non-trainable. It's pretty much like if we view Fourier transform as a change of basis, then pretty much these 2 matrices are just a non-trainable, and it has a complex part and a real part. That's it. And moreover, so we want to linearize it because this matrix is n by n. Okay, so this matrix is n by n, this matrix is n by d, and n is a sequence length, and it has this quadratic dependence, and people are just, starting from 2 years ago and starting to linearize. What they linearize means is they try to reduce the cost to linear dependency with the sequence length. There are 2 main approach in linearizing the transformer. The first one is the first 3, actually, the first 3, and the second one is the last 2. So the first 3 leverage a feature map. And this one is, they try to do some, near field or far fields. For example, this one, the fast multiple is, they try to exploit the low rank structure of the attention. Okay. And for the first attempt, okay, is to leverage a single feature map. So originally we had 3 learnable feature maps, right? And now they said, okay, so we only want to use a single feature map so that we can approximate the softmax. If we can do that, basically it's like a tensor product rewriting, so we can pull, because it's a single feature map, so we can pull out and we get a complexity down to the linear dependency. However, when I view this linearization, I got super excited because why not we take the row-wise view of this latent representation. So for example, in natural language processing, it's like machine is, so this is like, they have some token for this word, and this token is embedded for some high dimensional space. So their spaces are like a 512. So here it's like a simplification of it. And the learning is embedded to another, like this feature vector. However, if I view it as column, So this is like the column is like the basis, and the column space of the latent basis. Basically, I review it as like the sampling, discrete sampling of Hilbert spaces. If we view that, we can use a tool I learned from the finite element. So that was what I did back in like February. So, and then we have this nice, because then the nonlinear approximation, so, or say the universal approximator, this neural network, we can treat it as a linear space. So neural network is not linear at all. It's not a linear space, okay? But if we plug it into the attention mechanism, it becomes sort of linear, but it's still a nonlinear operator. And we rethink this, so we just reshuffle the matrix product. We do K transpose and V first. So we ignore the decoder part. We only consider the encoder. We only consider the matrix product of this, and this is a D by D matrix. And this suddenly reduces to linear dependency to the sequence length. And if we rewrite this, okay. And I say, hey, this is nothing but finite element. I mean, this is like a stiffness matrix or mass matrix. So then I went on to prove some simple theorem. I mean, once we realize this is a learnable Petrov-Galerkin projection. So if we assume these are orthonormal, but we don't have to in the end. If we assume, certain things, once we realize it's a learnable Petrov-Galerkin approximation, then we can just apply some standard finite element exercise to prove its approximation like a capacity. So for example, we have some consistency term that tell us how good this approximation space is. And then this corresponds to like a Stokes flow problem, a saddle point problem. And we have a nice interpretation of the key query and value. That is the query is like a function comes to us, asks us, hey, can you approximate me or give me a best like a representation in the latent space? Then the query got matched to the test space, which they called like a keys. Okay, so after the matching, the coefficient determines how we use value to approximate it. So the value is like our trial function space. And then we can simply use the discrete inf soup condition to prove this, and this C is our inf soup constant. So like I said, it's once we realize it's a Petrov-Galerkin approximation. Proving this is just a simple exercise of finite element everyone can do. So first, we prove the inf soup condition. And for the simplest scale dot product attention, it's a standard exercise of linear algebra. And we assume the key space is bigger than our value space. So, so we can find basically if the query comes, we have enough keys to unlock the best approximator. And then we apply the inf soup condition. Okay. So after we apply the inf soup condition, the rest is just to prove the best approximation when we minimize. So the theta is like parameter of our this deep neural network by one layer, and this one is nothing but a saddle point problem. So, and the saddle point problem is just this mixed problem. So if we solve this mixed problem, and by the way, this mixed problem is not as difficult as the Stokes problem, because the Stokes problem, the divergence matrix is not full rank, but here that we assume the divergence matrix is full row rank. And once we do that, we can see we can explicitly represent this Petrov-Galerkin approximation by the QKV. Okay, and this data is our basically nonlinear approximator, which is represented by theta. Okay. So and we have two matrix which are the Gram matrix. So we have this lambda and m, so as our normalizer. So inspired by this, okay. So here is one more slide. So but when we directly remove the softmax, even though we had this nice approximation result back in this February, but when I tried to apply directly, the result is even worse. So it turns out someone already like discovered this, removing the softmax, but they didn't. So in their paper, they didn't report the numerics on simply by removing the softmax because it doesn't work. Removing the softmax will degrade the numerical stability like huge, okay? And it doesn't work, all right? And inspired by the proof, so can we improve it? So the answer is simply, can we reinterpret these two normalization to some learnable structure? For example, then we propose this simple Galerkin attention. Okay, so like a Galerkin projection, we apply the layer normalization here. It turns out this year someone else already discovered this concurrently with our paper as well. So we simply apply the layer normalization after we do the projection. So this will greatly tame down the numerical stability. The other trick we use is based on the approximation, universal approximator, and our function is like the function we want to approximate is a function of the positional encoding. So maybe we should just, enrich this positional encoding in every layer. And it turns out Google DeepMind discovered this as well concurrently in their July AlphaFold 2 paper. And in the invariant pointer attention, this 3D coordinates these reference frame. It's like a reference element is being enriched in the attention layer, every layer. So, and after this trick, okay, we apply this problem again. It's not bad. We get like a tenfold improvement from the original. The classical, the vanilla transformer, or say the softmax removed. And it's not much slower than the Fourier neural operator because right now we have 3 learnable matrices now, and we match the parameters. What happens? But the question is, can we improve it even more? Okay, so inspired by some other literature, for example, if we rewrite the attention as a neural ODE, this type of integrator scheme, it makes sense to dial down this scheme like a real ODE integrator. And it turns out someone else is like in Schmidhaber's lab, they also discovered this trick concurrently. So basically we dial down the initialization of the projection matrix so that, and then we let the optimization take over and we add this a small diagonal matrix. So the projection matrix, a diagonal dominant is also implied by the proof to keep the approximation capacity if we have a good set of bases learned. And once we apply this, we also compare with the DeepMind's model. So, and Google Brain's model. So the performer is basically we apply their attention as we can see the Galerkin transformer if we only train 100 epochs. So all these models are 100 epochs and the Galerkin transformer is still the best. And also I would like to mention that if we apply all these tricks to the standard softmax transformer, it's getting much better as well, but not as good as a softmax removed. And if we train 500 epochs, so we can half this number, but I don't think it's worth it because our training just gets 5 more times. So that's why I only reported 100 epochs, but in the code, I mean, we're welcome to train 500 epochs. So I think no one currently can top this result right now in this simple benchmark. And in the 2D benchmark, we have, we still took the Caltech group's data set and the coefficient. So here, this is a coefficient. Why it exhibits this random, this type of pattern is because this is a covariance matrix. It's a solution to the Newman problem. This is a Newman Laplacian. This is like a L2 term. It's a Newman Laplacian. So as we can see, it's pretty smooth. So the covariance matrix is pretty smooth, and this is a push forward. So this function psi is just basically takes 2 values. So what happens to this map if we use Manila like plain English to explain is we only have 2 values, okay? And at a point around it, most likely it's going to be the same value, but it has certain probability to jump to another value. So we'll see this random interface, but the solution is going to be smooth. I mean, because of the elliptic operator. So we'll see the random interface, but the solution is going to be smooth. So this is like our training data. And then in 2D, so our feature extractor, we basically use interpolation-based CNN, and we use a multi-head simple attention. We still concatenate like positional encoding in each layer, and we add this smoother from the Fourier neural operator. So basically, the Fourier neural operator takes about 2/5 of the parameter. This takes 2/5 about the parameter. The CNN takes about 1/5 of the parameter. So, and this is our result in 100 epochs. Again, our model performed the best. So, and then the next one is we try to reverse. Okay. So we try to reverse the prediction and the coefficient. So it's like originally the model takes this as input and gives us this as the output. So right now we take this as input, this as output. So we try to, our model tries to infer the coefficient back from the solution. And so this is our result. So we simply, so this time because our like target is not smooth. So we basically remove this Fourier layer as a smoother. We only use this Galerkin transformer encoder, and we stack like 10 of them, and with D equals 128, and this is a result. So, but as we can see, if we have noise, it was pretty bad. So if we have no noise, the result is kind of good. If we add 1% noise, as we can see, because of the worsened Lipschitz constant, and we had this noise got amplified by the operator itself, as well as the black box model. So this evaluation accuracy is it's not very impressive. So recently, I copied some of these guys' code. So from GitHub, I readapted it to a 2D model. So this number got reduced. So this was the original model. So right now I implemented a multi-dimensional model. So this number got reduced by 260 times 10 to the -2. So it was much better. So if we apply a multi-level model, I think that the community start to shift in this direction. For example, in the transformer, this is a paper earlier this year. It's basically like a 2-grid transformer. So I think the multi-grid, so the community will eventually embrace this multi-grid transformer if we have multi-level structure in our problem. And that's it. So, oh, sorry. So we have 2 more examples, sorry. So this is Navier-Stokes. So I took again, we took the Navier-Stokes data set in Caltech Group's data set. So again, the Galerkin transformer performed the best. And however, I would like to remind the Fourier neural operator still trains the fastest, even though the Galerkin transformer is much faster than already the softmax one. So, but the Fourier neural operator, I think, still is trains fastest. And the last one is a natural language processing model. So we apply our this Galerkin type layer normalization to, like I said, all the tricks we discovered during this study. We apply this to the traditional language model. It turns out for this simple data set, okay, this data set is not as big as Wikipedia's data set, but and it has many infrequent tokens. So it has a ceiling. The ceiling is about 30. So the blue score's ceiling is about 34.5. So so I would like to emphasize that if we apply these tricks, so the training is much faster, and we have to keep the softmax because the decoder needs softmax. So the encoder part, it's better to keep this latent representation consistent. So we kept the softmax. And that's it for my talk.
Thank you, Shuhao, for your wonderful talk. Is there any questions from the audience?
Yeah, hi, may I ask a question? Hello?
Please, please.
Yeah, thanks Shuhao for a wonderful talk. My question is, in your framework, because from my point of view, I suppose neural network should be a universal approximator, or I should say the global approximator. But for the final element Galerkin derivation, it bases are local. So what do you think of their
Okay, that's a good question. That's a good question. That's a very good question. Actually, I addressed this in the last page of the paper. So the answer is it's not local. So if we think about it, because if we think about it, this dimension, okay. So if we think about in the finite element method, the bases are local, but if the bases are learned, it's global. So we can think like a global mesh-free basis, but under the Galerkin framework.
So your basis is still global, but
yes, the basis is still global. That's true. But we can still use Galerkin method. So it's like we can project whatever our solution to the column space spanned by this basis. So it doesn't have to be local. So the learned basis, I think in the paper, so I extracted the basis function. So where was it? So here, okay. So this is a basis function. So this is a basis function in the first few layer. I forgot which layer it is. Oh, okay. So in the first layer, this is a basis function, and this is like a later layer. As we can see, the basis function are much more smoother. But the bases are global. It's not local. The learned basis. Once we learn these bases, it's not local anymore.
Okay.
Mm-hmm.
Yeah, thanks.
Yeah, can I answer a question? Hello. Yeah, so my question is, firstly, so in this theory here, does that include the error from selecting the basis? I think your bases are automatically selected, right? So here, like if your basis is not aligned with the, maybe I would say the ground truth space. So is that error kind of included here?
This is error. We have a consistency error.
Okay, that includes the basis selection error. So maybe, for example, okay.
So it's like so this error characterizes so basically this is like a stability result. So in the finite element, we have our stability. So it tells us once our operator is bounded below, we can recover the Galerkin projection. Okay, but it doesn't tell us how good our approximation is. It only tells us we can recover the best approximation, but it doesn't tell us the best approximation is actually close to the actual function. If we think about it, for example, in the Stokes, okay, so if we choose an incompatible pair, even though, okay, so okay, Stokes might not be a good example, but if our so we can choose like a garbage basis, okay? And we apply the Galerkin framework, we can still get the best approximator, but the best approximator is pretty far away from what we would like, okay? So this one is like a characterized, like how close our current approximation space is.
Okay, so this one includes not only maybe the low dimensional approximation, how is that close to the ground truth, but also includes maybe like say the linear layer, things like the how do you approximate in this low dimensional space? Is that?
It actually doesn't include. So this is like I said, it's only a stability result. So because I'm not an expert in universal approximator, so it's like if we apply, so it's like so this is like a pretty preliminary result.
Oh,
so the universal approximation theorem is actually applied on these two. So it's like I haven't applied any neural network approximation in this. So it's only a stability result. So the neural network's universal approximation will be applied here.
Yeah. So then my another question is, if you use something like maybe SVD or the method of moments to choose.
Yes.
Yeah,
That's it works. Okay, so that's a good question. So I read so these guys' paper, they are using SVD. So let me see. Where is it? Oh, here. So they are using SVD. So their data is trained after apply this SVD, and even though we have many data, and the dimension is kind of huge, okay, but because of the low dimensional structures, the SVD it turns out it's not that expensive. But there are people using SVD, but the SVD cannot. So simply using, so we use SVD on the train. We use SVD on our target, and then we try to do some simple like linear model between the SVDs of these two, and but the result is good, but they cannot reach the level of black box model. But it's much cheaper though. So because it doesn't need to be trained like 100 epochs.
So that means you have some generalization error. Is that?
Yeah, but still it's a generalization error. So what I'm talking about of the SVD is like so. For example, in this paper, they do SVD in the train, they do SVD in the test, and they do SVD in the target, and they try to fit. So basically, they train a linear map between the SVD, between the train data and the train targets SVD, and then they apply this linear map to the test. So that's what this paper does. And then they tried to replace the SVD by some simple neural network. But it's not as good as a black box model, but it's still pretty decent. I think achieve decent accuracy.
I see. Cool. Yeah, because I think at least some version of SVD, like the method of moments, you can actually have the error bounds with respect to the noise. So that might resolve the large noise. I mean, your stability issue with respect to noise that you covered here.
That's true. That might be true. But recently I've been working on this EIT problem, and with much more data and the interface. I tried SVD, but my workstation has only 128 gigs of RAM, and it cannot handle, so I think I have 14,000 something data, and it takes up too much RAM when doing the SVD. Then I kind of give up. But that's true. SVD can reduce the noise a lot, actually. Like you said, especially in their paper, they actually mentioned that it might be promising for the Bayesian inverse this problem, but when we have this more data, I think SVD becomes somewhat, so it's problem dependent, but SVD is good. But I didn't apply it here.
Okay, I see. Yeah, and another question is, have you tried any example that maybe the ground truth kernel, for example, the Green's function, it's not like say invariant? So for example, I think in the Fourier, in the FNO, I think one of the assumption is the kernel satisfies like kxy is equal to, depends on only the distance between x and the y. So have you ever tried, does your model, can your model handle things like that?
The answer is I haven't tried. If the kernel function is like a weird thing. So right now, as we can see here, because at least for 2D, this PDE. So how to answer this question? I tried something, but it doesn't work, so I didn't report it.
Okay.
Yeah, that's something. So that's something. There's some secret. So the secret is the kernel. So basically, if the kernel is non-learnable by the Fourier layer or any like these transformer layer, so we can do some sneaky things to make it work. So as we can see here, if we reinterpret this as basis, right? If these bases cannot learn, or say a non-kernel, or say others, if we know a priori information about the problem, we can sneak some basis into the latent representation. For example, we add like a small scale, we randomly add like a scaled basis into this latent representation. Suppose we know these bases. Okay, so that's a huge assumption. So that's not good. So suppose we know these bases, then we can make it work. For example, I constructed a data set. I forgot. Oh, here we go. So I constructed data set. So this data set, I think I tried everyone's model. It doesn't work. But if we sneakily add the basis using the base, so we ran. So as we can see, the initial condition, the sample randomly follows the distribution, but the distribution only I know. So if I know this distribution, we can manually add bases to the latent representation, and it works again. So, but it's not ideal. I mean, like I said, if the model is not like a kernel, so if the model is not generated by a green function, and affected by something else, if we know a priori what the problem looks like, we can sneakily do this, basis enriching thing and make it work again.
I see.
But I didn't report it. So,
okay.
I have a similar question on the easiest way to break FNO is to run a very simple linear advection equation, like du dt plus du dx equals 0. And you take an initial waveform, which is a square wave.
Yeah.
So just as that, so we compare DPONet with FNO. FNO gives like 50% error for that equation. DPONet gives like 0.3% error. So you have like at the first glance, can you interpret such a result? Is that because it's not because of the discontinuity, because you have enough linearities there to handle that. But what's going on? Why FNO breaks down like that, 50%?
I don't know.
At Brown, we call this a Brown equation, the Gottlieb equation. Very simple.
I don't know.
Okay, that's something to think about it. But just for your information, DPONet was published first in 2019, before FNO. And the way, if you look at the theoretical paper of Mishra and with me and also with the Caltech people, you can see that we believe, and I think that's what the theory shows, that FNO is a special case of DPONet. So, a little thing, you spent too much attention to FNO, but we have a new paper coming out on 16 benchmarks. We beat FNO on all of them, okay, unlike what they say. And even though FNO with steroids, just like you were trying to do FNO with steroids, that's what I call it, still we beat. So I would be interested to compare with your regularization, the projection, to see how much that. So we call that the. I'll talk to you offline. Maybe we can do some comparisons.
Yeah, thanks. I'm looking forward to it.
Yeah, but start with this, because ut plus ux equals 0. You have to be able to get solutions for that to be credible. Because how can you do turbulence if you cannot do ut plus ux equals 0?
That's true.
That's an ongoing argument with them that they said they solved turbulence. It's not really turbulence. It's some sort of
Yeah, but I think so. My view is that the way Caltech group generates the data, it's pretty much it's like in their arena.
Yeah.
So because it's a Gaussian random field.
Right. So we need to be a little more. No, we use also Gaussian random field. That's not the problem.
Okay.
Gaussian random field is not a problem.
Mm-hmm.
It's what if you use a small correlation length, that would be a problem.
Oh, I see. Yeah.
Yeah. So there's lots of issues there. For example, with the Navier-Stokes, they just map like it's a scalar equations, really.
Yeah, yes, that's right. So their model is, even though everyone is trying to compare with them, I don't like I don't like I don't like Caltech group's approach at all, because I'm a finite element guy. I think this is verticity is I don't like this formulation. I prefer velocity formulation, but I don't think it's I don't think right now. So at least as far as I know, like imposing the divergence-free condition as what's happened in the finite element, I think it's very hard to impose these divergence-free conditions for black box model. For example, like a Lagrange multiplier. If we use this compatible pair, this this RT pair, and for the Navier-Stokes, I think it's hard to black box model to achieve those sort of like this divergence free to this compatible discretization of this type of a vector equation like Maxwell or something else.
Yeah, there are lots of holes. I mean, there's the story is, I mean, you present as a good story, but the story is much longer than that. But thanks for taking the time today.
Thanks. Yes. Thank you.
All right. Thank you, Shuhao, for your wonderful talk. So it's already 1:07. So let's move on to our second speaker. Just give me 1 second. All right. So our second speaker is Nick Winovich. So Nick received his bachelor in mathematics and Spanish at the University of Notre Dame in 2012. He then completed a master in mathematics at the University of Oregon in 2015 and went to pursue his PhD in mathematics at Purdue University under the supervision of one of our former Crunch member, Dr. Guanglin. And Nick is currently working as a postdoc at Sandia National Labs, researching machine learning applications for digital twin systems under the direction of Dr. Bart van Bloemen-Wenders. So today, Nick's going to give us a presentation entitled Operator Networks with Predictive Uncertainty for PDEs with Inhomogeneous boundary conditions. Yeah, so yeah, please go ahead, Nick.
Great, thank you so much. I appreciate the introduction and the opportunity to present my work here today. Today I'll be talking about deep operator networks and in particular the possibility of equipping them with some form of predictive uncertainty. This is a collaboration with Dr. Liu and Dr. Guanglin, my PhD advisor. And first I'll start off with some high-level overview and background. I'm sure everyone in the audience is more or less familiar with the ideas of operator networks by now, but just to make sure, I'll give a brief overview, and then I will go over two different ways that I have looked into for developing a UQ framework on top of convolutional PDE models and then the DeepONet, the fully connected DeepONet model, and hopefully have some discussion about how we can improve the UQ extension that I am currently working on, as I'll get to at the end here. But to begin the research kind of overview, the setup for the operator network training procedure is that we're going to offload training to a one-time procedure offline by creating a database. So the data generation will consist of specifying some type of problem setup, generating data for that, and then computing the solutions. And once we have that database, we will calibrate our model by giving an architecture, a network design, defining a loss function. In this case, we want to think about using a loss function which captures some sense of uncertainty in addition to the accuracy, and then training just using standard stochastic gradient descent in this case. And then in terms of inference, what we're looking for is to have a model which generalizes to both unseen and out of distribution examples, so that this is somewhat reliable and something that is very fast. So the advantage of the offline training is that when we are performing inference, the task only requires one forward pass of the network in general, although we'll talk about that more in detail. There's no training required, so it's typically much faster than some of the other approaches, the non-operator approaches. And then finally, we want to assess or have some confidence in the uncertainty predictions that our model produces. So to begin, since the primary thrust of the talk is based on this idea of predictive uncertainty, I want to motivate that. And this came about, to me, it was naturally motivated by the idea of Gaussian process regression or kriging, which I had studied earlier in the context of probabilistic numerics. And I wanted to see if we could possibly use some of the insights from that field in the context of neural networks. So just a quick review, the basic idea is that given some set of observations and also some priors, we have a quick way to update our model. So we have this updating procedure, and the way that we can tune our model or actually perform regression is effectively to calibrate the model parameters theta by minimizing this negative log marginal likelihood. And the benefit of this is that we have a way to calibrate both the model prediction and the uncertainty effectively simultaneously. So this is a great property. We have very robust uncertainty estimates from this framework. But unfortunately, there are a few terms that make the scaling of Gaussian process regression intractable, or it's basically just not applicable in a lot of context. So I wanted to see if we could potentially employ something like this way of training in the context of neural network models. And so the first attempt was back in 2019. Where I worked on this convolutional PDE model and considered a number of different applications. And in particular, one of the most important things that I was stressing back then, and I don't know how relevant it is in the current literature, but I wanted to see if we could create some flexibility in the domain that we were working with. So this setup is actually designed to be not independent, but to learn a distribution of meshes or domains, and it can predict solutions on different domains after just one training period. And the original idea was that maybe this would help avoid some of the competition with the existing numerical methods, because I know, like, if you're on a square, there are a lot of times you can use something like multi-grid. There's a lot of kind of competition. So just to be safe, I wanted to see if we could add this flexibility, and it turns out that that is in fact possible. So in a broad context, we have kind of this varying domain. So this will be one of our parameters to our problem. We have a source term or a source term and some other additional stiffness term perhaps. And what our goal is to predict the solution U. Now, because the domain is varying, I should mention we always are considering homogeneous, and in this case, Dirichlet, and also we can use homogeneous Newman boundary conditions, but that's really a matter of just how we input the data. So I just wasn't sure how to discretize the boundary other than giving a sparse representation in this kind of grid format. But that's the second point, is that we also are under this constraint that we're working with grid data. It can be an irregular domain, but our samples will be placed on some form of regular lattice, which will look something like this. So we use a higher resolution, but we effectively have a discretized version of the mesh, which is also stored so that we can calibrate our loss functions. So basically, we don't want the loss to penalize the neural network outside of the domain. And so we store this in an array format based off of the finite element meshes that we randomize, so that we're not getting penalized for irrelevant predictions effectively. And so we randomize a basic set of polygonal domains in this bounded region. So -1 to 1 is this kind of bounding box, so to speak. And we sample random domains within that, and then generate source terms and also stiffness terms based on Gaussian random fields. And if it's a stiffness term, we obviously apply some coercivity constraint and force that. But we also consider a number of different length scales just to see how the performance changes with respect to the difficulty of the problem effectively. So these lower length scales are more difficult, more oscillatory, and then the highest end length scale is kind of these easy problems where the functions are effectively smooth or very smooth. So after we have the source, we generate our solutions, and to do this, we use Phoenix. And one of the things I just want to emphasize about this is it's really easy to parallelize. It's trivial effectively, because all of these problems are independent. And so we can obviously just compute one problem basically on one processor and then another, and then gather our results by saving them and potentially compress that at the end. But what I found the easiest to do, and this is mainly just if people are curious how to generate these data sets on more cores, in Python, it's very easy to use the multi-processing, I guess, toolbox or the package. And what I found that works the best is to effectively partition the IDs or to enumerate the data examples that you want to generate, and then assign the processors batches of those IDs and generate the meshes first, so you can randomize the meshes. Based on that, you can use a GP method, so something like a Cholesky factor multiplied by a vector of unit normal variables to get the source terms, but then it's also important to project that onto the mesh. So there's this kind of dependency. So you have to project that onto the mesh and then compute your solutions using something like Phoenix. And to do this, I should mention that you do want to save like both your FEM, your XML format, say, and your NumPy array format. But at the end of the day, the benefit is that you can actually parallelize this very efficiently. And so like currently I have something like 60 cores, and it goes basically 60 times faster than if I were just using one. So it's a nice workflow, and it's very easy to use if anyone has any questions about that. But once we do that, what we get is effectively a database. So we have our meshes, our sources, and our solutions, and we want to provide our neural network with information about the meshes and source terms and predict the solutions. But to motivate this or to justify this, and my original inspiration to use convolutional networks comes from the idea of the existence of Green's functions. So in at least specific cases, we can think of these Green functions as defining an explicit solution mapping, which is defined by a convolutional integral operator. And so this convolutional integral operator, as the name suggests, kind of motivates this idea that perhaps we can apply some type of convolutional filter to approximate this, or some series, since we need nonlinearity. And in the paper, the Comp PDE paper, I show that this can also be used to establish the the applicability of basically the neural network approximation for PDEs. So you can use the maximum principle applied in addition to the standard universal approximation theorems with some interpolation and projection in between. But what this gives us is a way to basically discretize the problem so that we're back into this image-to-image setting. And so this has benefits and drawbacks. But the main benefit is that we can use existing architectures and things from computer vision and state-of-the-art techniques at the time in 2019 to make a robust model that's able to parse this kind of irregular domain and quite noisy or relatively noisy input data and to produce an accurate approximation along with some uncertainty. So the general structure is just an encoder-decoder model. It's also using UNet connections, which basically just share information from the encoder with the decoder. And the only real novelty on the network design is that we will take at some point in the decoder, we will split that into two branches, one for a mean prediction and one for a uncertainty or a standard deviation parameter effectively. So we'll get these two arrays for these pointwise mean and uncertainty estimates. And we need now to inform the network that that's how we want the network to interpret those two arrays. So we need to basically enforce this, and that is done typically through the loss function. So that's one of our primary ways of telling the network what our goal is. And in traditional learning methods, we typically use something like a mean squared error. So basically, given our estimate, we define a loss quadratically based on where that true solution lands. And then again, we use the mesh template file here to just filter out any of the regions or the points outside of the region of interest for our current target domain. So in contrast to this, I wanted to follow the Gaussian process regression framework a little bit and see if this may work. And what I came up with was the idea that maybe we can just think of these as independent normal distributions for each of those pointwise predictions and take the negative log likelihood as the loss. So this kind of probabilistic or probability-based loss is defined. It's very similar in a lot of ways to the standard squared error. If you're looking at the expression, it's just rescaled by this uncertainty or this confidence measure, and then also has an additional term related to that confidence as well. And so what this allows the network to do is to begin with these somewhat coarse or low confidence predictions, and over time build confidence to attain higher likelihoods and therefore lower losses in the at the end of training. And we actually see that this does occur.
I ask you, sir. Hi. Hi, my name is Apostolos. I'm from Brown. So your data that you're using for training, the source terms,
yes,
are they noisy as well? They come from a GP, but do you add any noise to them as well?
I do not in these results. I've experimented with it a little, and I've actually kind of done it on accident by making the jitter too large. So they were not very good samples, but it still works, but I can't report any like precise numbers. But these are clean, non-noisy.
Clean, yeah. And so the uncertainty of the network here, what does it represent?
So it's designed, and I have trouble narrowing in exactly on something interpretable to say here, but the way I think of it is it's basically calibrating the model so that on average, the distribution of errors, which is empirically, you can observe it to be normal, is captured. So at the end of training, and I can show this later in like the DepotNet slides, and there will also be some analysis here, but at the end of training, you can almost think of it like the end of an MCMC, like the loss associated with each point, the way that it fluctuates, because it's always changing as it sees different examples, it looks like something like the tail of an MCMC sampling procedure. And if you plot a histogram, you will see, at least in the examples that I've been working with, a normally distributed plot of errors. So they're typically a normal distribution of errors. And my thought was to fit that. What that means, I would say it's basically the model's uncertainty or the stability at the end, something to do with the geometry maybe of the convergence. But other than, I mean, I can't give you like a precise intuition to what that means.
I see. Okay. Thanks. And one more thing. Why did you select the autoencoder architecture? Why not just the CNN, for example, or something else?
Yeah, so the CNN was really based off of Green's functions. I had started this really just thinking about Green's functions. That was the whole start. So I was just starting to dive into machine learning. But at the time, the VAE and the GAN, so I started this maybe in like 2017. This was quite a while back. But the VAE and the GAN were the two, I mean, two of the biggest models. And the GAN is just a generative model. So that couldn't perform inference tasks. So perhaps in my naive interpretation of the field at that time, the limited information I had, I saw the VAE structure as one of the most promising ways to perform inference, which is to say, process something down to a latent space and then generate some prediction. And this isn't technically a VAE, but an encoder decoder, a prediction which is also spatially structured in that same context. And so I will say that the motivation for convolutions is that they are spatially aware in the sense that you are actually parsing features regionally, whereas if you use fully connected layers here, there's no spatial awareness. You could just re-index the entire input, right? And they're also dense and slow. So
okay, but yeah, I was asking because you are not using the encoder and the decoder like separately. After you're done, you use it as a whole thing, right? As a whole black box that, you know, gives you the results, right? You're not using only the encoder or only the decoder. Okay.
Right. So in my experience, though, this bottleneck, this data compression, so
it seems to help.
It usually helps. And yeah, basically what you can think of is the data gets about half as small. So we like double the number of channels, but we decrease the resolution by 2. So that's like dividing by 4. So it just kind of slowly gets smaller. And I think that allows or forces the network to pull information out. Whereas if it was just the same information size all the way through, I think it's just there's too much freedom there in some sense.
Okay,
I see. Yeah, I mean, it's a little bit of just hand waving. But this network definitely, of the many that I've tried, works very well compared to a lot of other variations.
Thanks a lot.
Yeah, no problem. And so the interesting thing is that at the end of the day, and so I basically optimized this for MSE training. So I did all the calculations and everything, tuned all the parameters for MSE. But when I took that all those optimized, not the weights, but the number of layers, the size of the layers and all of that, and I just replaced the loss function with this probabilistic loss, it was interesting to me that in almost all of the cases, there was slightly better performance, even with respect to the mean squared error. So even though we're using the MSE as the loss, and this represents potentially enforcing the boundary conditions harder, which was kind of negligible in the results. But even though we're defining the MSE as the objective, somehow the network is not getting as good results as using this alternative probability-based loss. So I thought that was interesting, and it's certainly interesting that it's uniform across all of these results, but it's just kind of an added bonus that we get in addition to the uncertainty estimates. So if we look at the results, it's a little hard to see if we're looking just at the the solutions. But if we look at the errors and 2 standard deviations, we can actually see some of this pointwise uncertainty manifest. So, I mean, these are actually quite typical. I mean, there were certainly some where the uncertainty wasn't totally capturing the error, but in general, they really do capture the uncertainty. And again, this is like 2 standard deviations. So we have some points where it leaves, but that's to be expected because we don't want to be too conservative with our standard deviation predictions, but it really does capture a lot of the error structure. And we can do this without adding really any time to the performance. So that's maybe one thing real quick before I get to the inference speed, is one of the main motivations for this very simple architectural change and the simple switch to the loss is that a lot of the other models like ensemble approaches or Bayesian training add a considerable amount of time to inference if you want to get those uncertainty estimates. And so I was, and also the Gaussian process, just coming from that field, is very kind of interested in not adding any complexity if possible. And this simple structure adds almost nothing. If you're looking at the calculations, the number of flops used, this is a pretty trivial addition to the network architecture. And the change here, perhaps a little less stable, but using logs, log predictions, it seems to work fine. There's usually no problem at all in the convergence. So doing that does not add any additional speed practically. And if you have access to a GPU, you can certainly get much faster, but on the order of like 20 to 30 times faster predictions than even the finite element code running so that it's coarsened to have the exact or a little worse accuracy than the neural networks, just for a fair comparison there. So, but they're very extremely fast. And this is again, because we have offloaded training to this offline one-time procedure, and that enables us to perform inference very fast. And then just quickly, I'll mention that you can also perform, you can also use the same architecture with multiple terms, so like an A and an F, just by concatenating the A and F as the 2 channels of an input, and you don't have to adjust the network architecture at all. And I don't have a slide for it, but you can also provide U and F and predict A, and that works not quite as well, but still accurate. It's just maybe twice as bad, I guess. I don't know. But here we also see that there is a noticeable increase in the accuracy for the probability model, and that's also true if we switch to Neumann boundary conditions. So basically just a simple Laplace equation, or Poisson equation, but now we're using the derivative information at the boundary to be 0. And again, it has to be 0 because I don't know how to feed information in this convolutional setting into the network without fixing the domain. So I'll talk about that a little later, but you can fix the domain. The quantitative results, or the qualitative rather, results on uncertainty that I showed earlier motivate this idea that it seems to be doing something correct, but I really wanted to look in more to how this predictive uncertainty behaves. And the first thing that I'll just point out is that we really do have this strong tracking of the uncertainty, and particularly overtraining, like I mentioned earlier, it starts out being unsure, so to speak, uncertain, and it gradually gains confidence, and it does so in line or well correlated with the actual L2 error that's being observed. So to get an even better idea of how this uncertainty is working, and namely to quantify some of those points that I had showed earlier where the error was actually larger than the uncertainty, I was interested in looking throughout our entire data set. So if we look at throughout all of our data examples and every pixel inside of the domains for those data sets, how often is the true solution within, say, 1 standard deviation or 2 or 3 standard deviations relative to our predicted uncertainty. So how often does this occur? And if we look at that with X varying from like 0 to 3 standard deviations, what we see is that both for the training and the validation data set, we get these very nice, very similar curves to what we would expect from a normal distribution being less than X. I guess this is kind of a little complicated, but basically this dashed red line, which you can barely see because it's being overshadowed by the validations data set, is what we would expect if we had a perfect prediction of our standard deviations relative to this idea of how much of the data set is within one standard deviation. So this is kind of like the 68, 94, 95-ish, 99 empirical rule. So this is basically saying that on average, our standard deviations do reflect an accurate representation of our error at the end of training. And what's more is that we can also think about replacing this normal distribution, these normal prediction model basically, with Laplace or Cauchy distributions. But what we see is that in practice, again, like I mentioned, you can actually observe these. You can plot them after just training your first time. You can plot what the errors look like. In practice, they always tend to be normal. But if you observe them to be Laplace or Cauchy, what I think I can take away from these following slides is that it should actually calibrate correctly. So in particular, I look at the idea of what happens if you inappropriately fit a Laplace distribution to normally distributed data. And what you can compute is the maximum likelihood estimator for that scale parameter B in terms of the standard deviation for the normally distributed data. And if we apply that correction, so we take the network's prediction, so if we were using a Laplace model, we would get this red curve. But the problem is the data, the true data, the blue and the orange are not distributed as a Laplace. So we need to readjust or rescale. And if we rescale by that maximum likelihood estimator, we actually get this black curve, which again coincides kind of right in between the training and validation data. And this same procedure can be shown in context of the Cauchy model. You have to do a little bit of optimization just to get the estimate.
Can I ask, can you elaborate a little bit on that? So how do you do the training? You still do the training with the Gaussian negative log likelihood?
No, thank you. I skipped over that. So you just replace the Gaussian, or the normal, sorry, or both, I guess. But the normal distribution here, you take this in the code and just replace it with this, or the negative.
So this is your loss function now?
Yes, and this is the loss function, and then this will be the loss function for the next. But yeah, it's just switching out the loss functions and seeing how the scale parameter, that basically that stem, that split part of the decoder, how does the network interpret that?
Okay, so although you are training with the Laplace loss function, the errors remain Gaussian. That's what you're saying.
Yes, exactly.
Oh, okay. Thanks.
Yes. Yep. Yeah. So we can kind of plot and we see the error distribution and it's still normal, but I just want to see, was it calibrating that Laplace correctly? And this basically gives us a sense, some kind of indirect measure that it does look like that correction term is quite accurate. So the difference between this red Laplace CDF and the black rescaled normal CDF, we can see that correction looks to be quite appropriate. And then also just doing similar calculations for the Cauchy model, we get a similar correction. And again, I think this is some form of maybe indirect validation. But if you have a data set where you're observing non-Gaussian error, which again, you can always just plot like histograms for, then you may be able to use one of these models based off of analysis of the CDF.
And how about the mean prediction? Did it get better or worse by using another loss function?
It was maybe slightly worse, but it was barely noticeable. So it was not that bad. It's just that the uncertainty was no longer trustworthy, basically. So the mean prediction actually still did quite well. And I think, honestly, it's basically just because it includes in some form, this mean squared or this L1 error. I guess in this it's a little less obvious, but there is this sense of the mean squared error being a part of the loss function. So I think that explains kind of why it's still able to converge.
I see. Mm-hmm.
Yeah, but thanks for the questions. And yeah, so basically these were just some kind of curiosities, like what happens in certain situations. But at the end, I felt pretty confident that there's some stability, there's some robustness to this uncertainty schema. And I wanted to think about how we may apply this to deep ONet. So again, with Dr. Lu and my advisor, Dr. Guang Lin, we've been working recently to take a look at how we can possibly add some form of this or some variation of this to the deep operator or deep ONet architecture. And so I'm sure that this is like preaching to the choir, but I just want to emphasize that the deep ONet model, I mean, it's very simple and in an elegant way, but I think this is not maybe emphasized all the time. What really we have is in kind of simple terms, a branch network which processes our input data. And in this case, I'm going to have input data for the interior and input data on the boundary. And so there's one neural network assigned to computing weights based off of that information, and another neural network, a trunk network, that is solely defined based on spatial coordinates. And because it's only defined on spatial coordinates, what we can do is think of the components of that output vector as basis functions. And that motivates this inner product structure enforced on the deep ONet output, because we can think of this almost as a FEM, an auto generated form of finite element method, or some type of expansion method where we have basis functions which are automatically learned, and these weights are computed based on what our input data is. So we learn these kind of global basis functions for the full data set, and then the other neural network, the complementary neural network, is assigned the task of basically computing the correct coefficients. So it's a really nice framework. And in addition to that, one of the key things that I should bring up is that it's using this notion of sensor data, which removes one of the biggest hurdles of the convolutional approach. So in the convolutional setting, we are really stuck to this grid. And that can be, as was mentioned in the previous talk, and I'm sure people are aware of, there's serious limitations, especially with how you can apply this in practice. So if you're actually working on an engineering problem, you most likely do not have a uniform array of observations. So one of the benefits of deep ONet is that it's able to do quite a bit based off of sensor data. And I will point out the one caveat here, and I'm interested in thinking of how we may be able to extend this, is that you require a fixed domain due to the use of sensors, but I think there's some ways to extend that. And please let me know if that is not the case. But the sensors basically give you freedom in the sense that you're mesh free, and you are not restricted to these uniform placement of observations. And since we're working with a fixed domain, that's what inspired me to try to think about how we can add some boundary conditions which are non-homogeneous, because that was one of the other serious drawbacks that I found when working with the convolutional approach. It was just awkward to try to feed this boundary data into a convolutional network. It's just too sparse. And if it was flattened, then we could do that, but it would have to be the same size for each domain. So we can still do a workaround in the convolutional setting if we have a fixed domain, but I really have focused most of my work here on the deep ONet setting, just to see how this compares. And again, you can see the input data, you can see like sensors located, and this is overkill. You really don't need that many sensors at all, but it's able to work with this kind of rough data and solve some of these similar types of problems. The Main difference, we have a fixed domain for each problem setting. So that's to say for each training, for each trained network, it's basically custom tailored to a domain. And that really makes sense as a constraint based on the idea that we're learning these bases for the domain effectively. But thanks to that, we are enabled, we're able to add this inhomogeneous boundary data and in-use sensors. So to start off, I just tried a lot of variations, and these are the ones that seem to make the most sense of how we can actually incorporate these boundary conditions. And after like dozens of different experiments, just trying to play around with it, the very simplest way works just as good as everything else. So they basically all still work. But you can really just feed in the sensor data from the interior and feed in the sensor data from the boundary and just forget about it. You don't need to really come up with any elaborate schemes for how that information is combined, which is not the case in the convolutional setting. And then after that was established, I looked at how can we most appropriately define an uncertainty extension. And this is where things got a little bit tricky. But what I found was there was really no benefit to adding this separate trunk. I came to the conclusion this first model doesn't really make a whole lot of sense because you're really reusing the same bases. So that's like assuming that your error profile is in the same space as your solutions. I guess it just didn't make a lot of sense to me logically. But what I was basically able to come down to or bring it down to is this slight variation, kind of similar to the convolutional setting where we just split the decoder. So we'll just predict separate weights for the mean and the standard deviation and separate bases for the mean and standard deviation. However, in all of these variations, every kind of format that I tried, I keep getting these quite noisy error profiles. So this is the final network structure. And what I was continuing to see was the error predicted by the network was extremely flat. And I couldn't understand why that was happening based off of my experience with the convolutional networks. We usually have some errors that are structured, and that enables this uncertainty. But when I looked at the error profiles, what I see is these converge very well to basically the same level and a little bit better than the convolutional networks in much less time with less data. So they have a large advantage. But the one caveat is that there seems to be, at least in these experiments that I've been running, this odd error profile, which is they're really small errors, but they're really unstructured. They're not kind of these peaks at inflections like the convolutional models typically have. And I think it makes sense in some regard because the convolution is using these spatially structured predictions with decoding and interpolation, whereas we are relying on fully connected layers for the deep ONet. But I tried a number of things like adding to the trunk network. So I guess I have it here. Like adding regularization to the trunk network actually gives you really smooth, and you can control it quite well, smooth basis functions, but I still was observing this error profile. And finally, I kind of sidelined that for the moment, trying to get these point-wise structured uncertainties. But what I found was if we just take a single scalar prediction, so now we're really not increasing the computation at all for the branch and the trunk, so we're just adding one value at the end, what we can get is kind of this function level uncertainty, this B sigma that's related to the input, the complexity of the input, and this domain level uncertainty, which is constant among input. So it doesn't depend on the data you're seeing, but it's just kind of spatial. And maybe if we had a more irregular domain, we would see more dramatic features in that. But for the most part, it was flat because our uncertainty was generally just kind of this kind of noise structure. Yes.
Excuse me. So why does it worry you, the fact that the error profile looks like this?
So yeah, it depends on your problem setting, but it worried me because I'm trying to equip it with uncertainty estimates. And now its goal is much harder than what I was looking at before. And the error profiles were consistently flat. So I still attempted, but the difficulty is that it's kind of going up and down and up and down. It's kind of all over the place. And unless I haven't.
But the uncertainty that you get from your network is smoother than that, right?
Yes, it's typically smoother, and yeah, because it has to have basis functions.
Okay, because in general, like in regression, across different locations, we do want the error profile to look random. Otherwise, it means we are missing something.
Right.
If there is structure, it means that we are missing something. So that looks good to me. That's what I'm saying.
Yeah. Okay.
Especially if your standard deviation that you get from your model is smooth, and it's calibrated as you say, then yeah.
Yeah, that's a great point. So yeah, I guess and that's really good to hear actually. But what I was concerned with was that if we wanted to represent this accurately, basically the number of basis functions would exceed the number we would need for the prediction, the mean prediction, right? And so then that would eliminate this kind of cost-free extension and really start to maybe make it questionable if it's useful. But that's a really good point. And as I'll show, there actually still is a good calibration of the uncertainty. It's just flat.
Yeah. Because if there was some structure, then this should go up to the mean. That's
right.
That's
and I think
like usually what we
smoothing. Sorry, but I was just going to point out. I think there is some. These are like inflection points, and I think it's a property. It's overly smoothed by the.
Yeah, because of the CNN, as you say. Yeah.
Mm-hmm.
Okay.
Yeah, so that's a great point. Yeah, so if this is not problem, I mean, yeah, that sounds great. But the takeaway was that one each is enough. So maybe this is a blessing because it's very low in terms of computational additional computational expense. And in addition, we can look at how it's calibrated and see how maybe this is working in a different way to that pointwise, although I guess I could still run the same pointwise analysis. But what I did was I would look at different examples, so FG pairs, basically input pairs, and I would look at the tail of training and see how the error was at random locations. So for each of these steps, I would pick a different location on the domain and just jot down what the error was and create a histogram out of that. And as I mentioned before, you can kind of see this is just normally distributed data effectively in most cases. And for a lot of the cases are predicted likelihood. So basically this is a Gaussian distribution with a scale parameter taken from the prediction the network has for this particular FG pair. And in a lot of cases, it's dead on. There are some cases though where it has a bias. So I looked into adding bias. I'm still kind of considering that, but it's always normally distributed. And if it's centered around 0, which it is for like 90% of the examples, then you get a good calibration. But there is this notion of some of the problems it somehow underpredicts the solution more than overpredict or overestimating the function values. But it really is quite accurate even on this kind of small sample size in a sense. But if we look at the general scale of the errors, we also see that there's really good generalization even outside of the data that we've generated for training. So here in blue, we have the uncertainty, the predicted uncertainty, and the actual error associated with the model on validation data generated in distribution. So these length scales between 0.2 and 0.3 were used to train. And we wanted to ask, how does that model generalize to easier problems with these higher length scales and these harder problems, these much harder problems as we're getting quite close to 0 with the small length scales. And what is nice is that although it's not perfect necessarily. And in general, we have kind of an overestimation of the uncertainty to some degree. It does automatically identify that these are harder problems, even though it's never seen those problems before. And it does not kind of freak out and say, we've never seen these before, because they're easier. It naturally identifies, the network naturally identifies that these are no problem. We can still work with these, even though we haven't seen these in training, these types of problems. None of these have been seen in training, but different samples from these function spaces have been seen, whereas these function spaces or the function spaces associated with these samples have not been seen. So we thought that was quite interesting. And then one last note, as I'm reaching the last few minutes, I just wanted to point out for anyone implementing DeepONet, there's one key, and I'm sure that anyone who's using this knows, but I just want to emphasize that if you use the training graph for inference, it's not very fast, but that's really wasteful, because you're going to use the trunk or compute the trunk over and over and over again. If you want to perform inference on arbitrary input data, so you're getting sensor data in some type of system like a digital twin or something, and you want to predict in real time, what you do is one time after training, you can create or compute the trunk weights, or these basis functions effectively, and also compute a sparse matrix, I refer to as a placement matrix, which takes your vector output and assigns it into this structured grid, if you want a grid, or into whatever structure. And this is kind of optional, but for most cases, if we want to visualize it, we can do that quickly by just pre-computing this once offline, and it's relatively negligible once you do that. But it's very fast in terms of prediction. And this is also, I think, 128 by 128. So this is about the same speed as what the convolutional approach is when you apply that to the same problems. And also another advantage to DeepONet over the convolutional approach is that conversely, if you fix the F and G, what you get, so you can do basically the same thing, but you can actually define your surrogate model in terms of a neural network, basically just a weighted neural network, and you can use automatic differentiation to get the surrogates automatically. And so that can also be used to add physics-informed training to DeepONet, as Rossi and others developed earlier this spring. So just in conclusion, I just want to say the idea is that we specify a system, we train offline, and then predict in real time with some sense of uncertainty. There's still some questions about what exactly that means, that uncertainty is capturing, but I hope that I've illustrated some of the notions of uncertainty and how it can be interpreted in these specific problems. And then I have just some concluding remarks, which I've hit on a lot, but both of these approaches provide very fast, flexible solvers that work on irregular domains. So we have really no restriction to a grid or it doesn't have to be a circle. It can be really quite general. And I think that sets it apart from a lot of the kind of pre-processed neural networks that are coming out. And the main kind of difference is that while the convolutional requires grid data and the DeepONet can work with this kind of unstructured sensor data, but because of that, it requires a fixed domain. Convolution can use this kind of varied domain, but that comes with the restriction that you need homogeneous boundary conditions unless you fix it. And then finally, we get a little bit more of a spatial UQ estimate with the convolutional approach. But as was mentioned earlier, that actually may be a sign that the accuracy can be improved further, and maybe that's not such a great thing. Whereas the DeepONet is really just giving us a function level UQ. It's giving us a nice smooth uncertainty, which is associated with those pointwise errors, and it's shown to capture the actual errors in practice. And then one final thing is that when you're working on fixed domains, DeepONet is much more data efficient. I should just clarify, you can use maybe like 10 to 100 times less data than the convolutional approach. So that's something definitely to keep in mind in addition to all of this. That's all I had. So thank you so much again for giving me the opportunity to present. And if you have any questions, I'm happy to take them.
Thank you, Nick, for your wonderful talk. So is there any questions from our audience?
Yeah, quick question from Thomas, Middle Tennessee State University, and my professor is Professor Khalid. I want to know, is the uncertainty over the entire trunk, over the entire depot net?
The uncertainty is tailored to your specific input functions. So for example, yeah, if this is your data, this is your specific data one time, you'll get one, and this is what I mean by function level. So it'll say, maybe this is pretty smooth. So maybe this is very accurate, so its uncertainty will be small. But if we get a very hard problem, then it will give us just a number, a scalar that will tell you basically how uncertain it is.
All right, thank you.
Nick, did you try to run like with different initializations?
I have not tried that. I can jot that down though. I can look into the initializations because I'm basically using the TensorFlow default initialization.
Maybe Shuhui, do you have any questions?
Yes, I have one question. This is Shuhui Meng. I'm a postdoc working with Professor Nickolas. So for DeepNet, so basically, when we talk about uncertainty, we consider the uncertainty caused by the incomplete data or noise data. So by in the DeepNet, so for testing, if you have say complete F, what's the uncertainty means in the DeepNet?
So it will basically give you. So here's one way to think about this uncertainty is, I could have chosen to stop the network at any one of these time steps, and I would have these kind of different errors. But on average, there's this kind of uncertainty. Maybe that's not technically the correct interpretation. So if you look at the errors at the end, and you're looking at the pointwise errors on the specific problems, or for one F and G, and you plot a histogram of what those errors are. There will be some that are too low, where the error is negative, some that are too high, and in general, it does give you this normal distribution. And what the prediction is basically trying to fit that that histogram. So it gives you like what your worst case error is and your best case. Although I wouldn't say it's like a really rigorous or trustworthy at this point, but the cross-validation is decent, it's good. But there are examples, like I mentioned, where the errors are quite higher than this one standard deviation due to a bias that somehow is incorporated in the mean prediction.
Okay, thanks.
No problem.
The question of what Nick shows at the end, that he makes the DeepNet very fast. You have a similar algorithm. You have also done this. Is it? Yeah, that one. Can you compare notes with Nick for your fast version of DeepNet versus his fast version?
Yeah, I would be happy to. And just to clarify, so this is like an einsum, like a vectorized version. So they're pretty simple operations. And this, again, is just a sparse matvec. And then really, I mean, these are like negligible in comparison to evaluating the branch. And I think evaluating the branch is just necessary. So I don't know if that can be sped up. So I think this is quite nice. And yeah, it's basically einsum does this, because these are basically these basis functions are these very long rows vectors, and we want to do like basically a row-wise multiplication by each of the coefficients, and then position them. So yeah, I found this works really well, but I would definitely be happy to compare notes and see what the alternatives are.
Shuhui, I think it's different. What you're doing, you put it on a lattice too, right?
Yeah, basically I use same grids, the same grid for each input and output, and then so in the original implementation of deep lab, we have to say train data, just fit one data or one data from one
Right.
function.
Right.
In my implementation, I can fit directly say multiple functions in the training as the mini batch.
Oh, so oh, but are you taking advantage of the fact that the trunk is computed in parallel? Because I think you're still
yes, exactly, yeah.
Okay, yeah. I think if you have a GPU, it's not a real problem. But if you're performing offline, I mean, technically, you're still using redundant flops. I guess is just a takeaway, because you're recomputing this for each to make each point.
Yes, one difference here is, this is Lulu. So one difference here is in Shuhui's approach, basically the speed up the training. So if we assume all the training data sets are aligned on the same sensors, the output sensors, then we can speed up training. But Nick here is speed up the inference.
Right.
Even if the training data set is random, it's unaligned, but in this way we can still speed up the inference. So it's slightly different angles. Yeah.
Right. Okay. Yeah, definitely. Thank you for the clarification, Lou. Yeah, you need to compute the trunk if you're doing training. So this is only for inference, like Lou was saying.
Maybe we need to put the two fast tricks together.
Yeah.
Nick, your code is on GitHub.
I think I shared it. I believe I shared it with Lou, but I can certainly share this implementation. This is really quick. It's really just, there are some caveats with TensorFlow. So you have to save different points in the TensorFlow graph. I'm still using TensorFlow 1. So you need to save a way to evaluate just the trunk and evaluate just the branch. But after that, I mean, this is already implemented in SciPy, a sparse, I mean, it's just mapping an index to XY coordinate, basically. But yeah, I would be happy to go through this code with anyone.
Yeah, well, maybe.
Yeah.
Yep. Okay, if there's no more questions, please thank our speaker again. That's the end of this week's seminars. Thanks for joining, and everybody have a good weekend.
Yeah, thanks. Bye.
Bye.